Hello, so in this video we will talk about forming of spanning trees through a breadth first search algorithm. Okay, so just a recap from spanning trees, that a spanning tree of a graph is a tree which has all the vertices of the graph G. Okay, and they can be multiple spanning trees of a simple graph, of a simple connected graph, but all of those all of those different spanning trees must have the same number of edges. And it has applications in multicasting, Internet Protocol multicasting, and it can also be used to find some simple problems like paths and circuits, connected components, cut vertices, articulation points, and also can be checked if a graph is bipartite or not. Okay. Okay. So now we describe the breadth first search algorithm. So what do we do in in simple words? We start with the arbitrary vertex as a root, and then we choose all the vertices adjacent to the root and insert them along with their corresponding edges in the tree at level 1. Okay, then we order those vertices at level 1 in any any order, any arbitrary order. Okay. Then for each vertex at level 1, we insert the adjacent vertices along with the corresponding edges which are not yet chosen into the level 2 of the tree, and avoiding circuits or cycles. Okay. So we keep on adding at level 2 then. So if we have 4 vertices at level 1, so we choose the first vertex and choose all the adjacent vertices of the first vertex which have not been inserted into the tree, and insert them in level 2, and so on. And we continue until all vertices are chosen. The process should stop since the graph has a finite number of vertices. So but the main utility of this algorithm is that you can find the length of the shortest path between any two vertices. So the length of the shortest path between vertices Vi and Vj is the level number of Vj when Vi is the root of the spanning tree found by the breadth first search. So if you want to find the shortest path of between two vertices in a graph, you make a spanning tree starting with one of those vertices and see the level number of the other vertex. Okay, so this is a very handy application of the BFS, or breadth first search. Okay, now let's do, before we describe the actual pseudocode of the algorithm, let's do the breadth first search of this tree which we did for the depth first search, and I just reproduced it here just for the sake of comparison. So let's choose our root as A again. We chose our root as A again. So this is just lowercase letters, but they mean the same. Okay. So let's choose A here. So we have A. Now for A we have only one adjacent vertex. So we have B here. Okay. So then for B we have C, E, and F. So we have C, E, and F. So this is my C, this is my E, this is my F. Then for C I have only D, and for E I have only J, and F is now done. So there's no vertex of F adjacent to there's no vertex adjacent to F which is not being covered already in the tree. Okay, so then for D I'm done for D as well. Okay, for J then I have so many of them. So I have K, so I can say K here, I can say GHI here, so G, H, and I here, and I can say P here, correct? Okay, so let me go a little bit up. Okay, so for GHI I don't have anything more to do because for GHI all of them are covered, all the adjacencies are covered. For K I have O, N, L, and M. So for K I will write O, L, M and N. So O, L, M and N. And similarly for P, I will write Q, R and T. So Q, R and T. And for Q, I will write S. Now note that I can say R, Q, T, and then I can put S here. But since this is my ordering is starting from Q, I have to put S there. Although, logically speaking, I could have put S with R or S with T as well. But since my ordering is Q first, R second, and T third, therefore I have to put S with Q. Okay, so this is the breadth first spanning tree formed by breadth first search of the same graph which we used to form the spanning tree through the depth first search. Okay, so what are the observations? So observations. Okay. Now a tree, an edge in G which is not in T. For a depth first search, what did we say? That an edge which is in G but not in T. T is what? T is the spanning tree. So T is the spanning tree we are interested in. So an edge which is in G and not in T has to connect ancestor and descendant in DFS. Okay, but for the breadth first search, it has to connect either two vertices at the same level or two vertices which are just one level apart. Now you can see that, for example, if you can see uh, Q to R is now gone. Okay, and Q and R are at the same level. Similarly, uh, G to H is now gone, and G and H are in the same level. Okay, and to C to F is now gone, and C to F are in the same level. Okay, what else? K to M is now gone. No, K to M is not gone. M to N is now gone. So M to N are at the same level. Okay, so there are cases. So for BFS, removed edges means same level or a level difference of 1. So this level difference of 1 you can appreciate if you try to make a spanning tree of a bipartite graph, like say for example K34. So this is a hint for you. So if you do that, then you will see that there will be some edges which are removed, which actually connect two edges which are two vertices which are one level apart. Okay. Okay, now this is for simple explanation and how to make a spanning tree out of a graph using breadth first search. Now we call this for the pseudocode. What do? We define it. We start with this: a connected graph with arbitrary ordering v1 to vn, and in the start we say the tree with only one vertex v1, and we have an empty list which is L. So first, what do? We put this root into the empty list, and this list is actually a list of unprocessed vertices, which will be clear while we talk about it. So we keep on moving as long as L is not empty, and we remove the first vertex, and for each neighbor or for each neighbor means vertex adjacent to V. So for each neighbor W, if that W is not in T and not in L, we put that W into the end of L and add W and edge VW to T, and then we continue until this condition is false. Okay, now let's see whether it makes sense or not. So for example, in our this example, so in the start my T has only A and my L has put A there. Okay, so then we say for each neighbor of A. So what is the neighbor of A? B. So is B in T? No. So we put B and the edge AB in T, and then we put, now A is now gone because we remove A from T, but then we put B in L. Okay. Now what are the neighbors of B? C, E and F. So C, E and F, all of them are not in T, not in B. So we put A, B, C, E and F, and the edges, I'm not writing them. So for example, I'll just write one edge BF, for example. Okay, and then L, I take out B, but then I put C, E and F. Okay, now note the order here. So now first of all I will check with C. For C I have D, then I put D there, A, B, C, E, F and D with the corresponding edges, and the last edge will be C, D, and then L will not have C, but it will have E, F and D. Similarly, then I'll check with E, and then I'll check with F, and so on. Okay, so this way I will keep on going until I will see L will be empty. L will be empty when I have reached this S here. Okay, so if pseudocode to actually program a breadth first search using a graph with a given set of vertices and given set of edges, this is what we have to do. Okay, and this you will appreciate that if we keep on doing this, we will get up exactly this uh, spanning tree if we start with the root A and we use the same ordering as I've used in the explanation. Okay, now let's do the complexity here. So as in DFS, we check each edge or examine each edge at most twice. Okay, one when we actually add it, and sometimes when that vertex is here, when we check for each neighbor, if W is not in T and not in L, so we check for that W not in T. For that we have to check the edge there. Okay, so then my order is again order of the number of vertices, sorry, number of edges, and number of edges is for a simple graph is again, we know that this is less than or equal to this number, which is a second order polynomial in n. So my complexity is order of n squared here. Okay, so this is it about a brief explanation of the breadth first search algorithm. Okay, and hope it was easy to understand, and thanks for watching. Hope you liked the video.